Okay, last lecture for chapter 19. We've already developed the equations. For example, third slide in. We've already dealt with these equations. We've dealt with the concept of entropy. We've dealt with the concept of Gibbs free energy. Second law of thermodynamics. We derived this guy. So let's put all this to use and for a chemical reaction, and show the predictive powers that we have in front of us with these equations. And what I want to start off talking about is this notion of a standard state, and you can see it listed here: pure solid, pure liquid, common pressure, 1 molar concentration, elemental form, and then also the temperature at 298 Kelvin. And what this is in reference to is these superscripts that you see for your different parameters. If you see a naught, this 0 as a superscript, that means that measurement, that calculation, that reaction is occurring exactly at the standard state. Now, this is, do I want to use the word idealized state? Maybe. It's very rare that you have a chemical reaction occurring at these different parameters. At all of these parameters, and specifically I'm thinking of 1 atmosphere and 1 molar concentration, especially of the solution. Typically, like in a biological system, really, when I was in grad school, millimolar showed up everywhere. And so we're talking about the concentration is 1,000 times weaker than that at standard conditions. So if we want to be able to use these equations that we've developed, we need to go beyond the naught. And I guess actually, let me do a little editing here. The way this is laid out, that would be an equation at standard conditions, and then you would see the 298 Kelvin there for temperature. But we want to develop a set of equations that allow us to, again, go beyond this condition of 298 Kelvin, and then, so this is a gas phase reaction. This calculation would be asking, well, what are these different values when the partial pressure for all of those components are at 1 atmosphere? And it's a good beginning step in terms of understanding the thermodynamics of a particular system. Remember, thermodynamics is going to tell us whether, is the reaction going to proceed that direction or not. It tells us nothing about how long it's going to take it to get there. That's kinetics. So if you're talking about time, that's kinetics. If you want to talk about just, the prediction of whether the reaction is going to work or not, that's thermodynamics, and how far to one side or the other is it going to work. And that's actually that predictive power, that notion of which side is predominating. That's a Kc or a Kp kind of calculation as well. So there's actually a link between chapter 15 and this chapter, and you will see it at the very end of this presentation. But what I want to do on this example is, this is purely at standard conditions. And so when you see this label, when I use this label, that means that all of these conditions are true. When I use this naught, that means all of these conditions are true. Any deviation from these conditions, then you won't see the naught. Or something else I do is I might put non-STP. I do that in a few places. Non-STP label. So something has changed that makes it a non-standard temperature and pressure condition. Now, just let me make a little comment here. It's actually an edit on the entropy equation here. This is a little different than the second presentation for this chapter. You may not notice the change that I'm doing here, but the delta is present on this side, talking about the reaction change for the entropy. the delta is now absent here and here, and actually I've removed the F subscript here, the entropy of formation. It was a typo. Actually, I think I scratched that out. Second video I scratched that out, but I forgot to mention the delta shouldn't be there. Those are absolute values, so you don't have a delta. So anyway, just a little side note there for us with the entropy change. How do we approach this problem? Well, actually, it's laying it out pretty clearly in terms of what it's wanting. Step A is telling us Appendix C. That gives you the tabulated data for all of these parameters for the different products and reactants that we're going to see. So really, it's more of a plug and chug game that we're doing in this first example. So in Part A, this is dealing with Part A, this is dealing with Part A, and then Part B, we're dealing with that guy. And again, the temperature is going to be 298 for this particular calculation. So again, completely standard conditions all the way through. Now, one thing I've done here is I'm not going to write everything out here. I'm using the computer to show you that these two calculations are going to come first. The next slide here, here's the breakdown for all of the steps. Okay, so here's what was on the previous slide, and what I've done is, if we remember it's SO2 reacting with oxygen to form, and I'm going to go ahead and establish an equilibrium state, and it's going to form SO3. And let's see, there are 2 moles of this guy, 2 moles of that guy, and 1 mole of the oxygen molecule. That's our reactions, of course. Product, reactant. Remember, when you're using that tabulated data in Appendix C, you're comparing, what's the contribution of the enthalpy from the products compared to that of the reactants. You subtract the two and it gives you the difference there for the reaction. And so here's the setup. Now let me draw a little dotted line between each one of these so you can sort of follow this as we talk here. I've used the subscripts to indicate here's the products, there's are the 2 reactants, and fortunately, remember the delta H and the delta G are both relative values. So that means that the enthalpy change of formation for elemental form is 0. So anytime you have an elemental form in your chemical reaction, you can treat that as 0. It drops away. And so there we have the 0 at that point. The numerical values, I've just pulled, see a typo, look at that. I just pulled those numbers from Appendix C. I'm keeping the units as is, kilojoules. We'll need to switch that here in a minute as we go through these problems. And then the 2 moles are simply from the coefficients for the reactant and the product that we have in our balanced equation. Plug and chug, and I get a negative enthalpy change. So we say this is an exothermic reaction. So this is actually going to help favors a spontaneous reaction. Now remember, spontaneous reactions, it's not just enthalpy you got to look at. You also have to look at entropy. Well, as it turns out, entropy has really the exact same form as enthalpy or Gibbs free energy. There we have the breakdown again, same layout. We have the reactants on this side, the products on this side. Notice the subscripts here. Let me just go ahead and throw in the dotted line so you can keep track of everything a little bit better. Again, the 2 and the 1 mole here coming from the balanced equation. Note now the big difference here is that, remember, entropy is an absolute value. S is 0 at 0 Kelvin. As you warm things up, and we're at 298 Kelvin, there's a certain amount of entropy that is contained, if you will, in the compounds as listed. And so all of the reactants and all the products will have some numerical value for the entropy calculation. So even though it's in its elemental form, it does have actually a substantial amount of entropy in that particular, in 1 mole of oxygen gas. And so, long story short, these are not going to be equal to 0 for the entropy calculation. If we do the plug and chug, now we have a negative value for the entropy. And let's look at that and how that affects the delta G calculation. I guess one thing I want to point out is there is a difference in the units here. This is in joules, and if you look back at the enthalpy calculation, this was in kilojoules. And so just be aware, you need to change one to the other, and I think on the next slide, yeah, what I've done is I went ahead and changed the entropy to kilojoules. So notice what I wanted to point out, the negative here. There's our Gibbs free equation. I'm going to edit this for you here. That's still a naught, indicating standard conditions. All I'm doing is pulling the numbers I calculated from the 2 previous slides and plugging them into this expression. And the point I want to make here is that the 2 negatives here, well, that's going to create a positive. And so what it's doing is actually the entropy part of the calculation is actually hindering the spontaneous process. Because remember, the more negative, the more likely it's going to be spontaneous. We'll put it that way. It's sort of a casual statement of what that means. So we'll just say more spontaneous. So if with this one, if we can actually see it in the formula. There's 3 moles of gas here. There's 2 moles of gas here. So just by looking at the number of moles, we sort of expected the entropy to drop here, for it to not favor a spontaneous reaction. And we see that in our calculations here. So with the decrease in entropy, what it's doing is it's making the reaction less spontaneous, if you will. This calculation was going through the mechanics for standard conditions. This example here, notice I've introduced this non-STP label. And where is it non-STP? Well, there's no concentration or atmosphere label, so that's not part of it. Remember, go back to the second slide. Right, concentration matters. There's nothing listed about that, so we're not like changing the concentration. We don't have to factor that in. We'll deal with that later. What's happening here is that we're changing the temperature. If we look here, notice that it's asking for the Gibbs free calculation at 400 Kelvin. So we're increasing in temperature, so the temperature is increasing. We're going to see, what does that do to delta G. And now, actually it's in the proper form here, what we do, even so, this is it's a simplified form here. We already know the numbers for delta H and delta S at 298 standard conditions. If we want to calculate the delta G at 400 Kelvin, I guess we could go in and find some more complicated formula and calculate these, but what you see is that these stay at the naught, and notice that all of the Gibbs free for this reaction, I've dropped the naught. And the reason why that is because we're at non-standard conditions. We're at 400 Kelvin. But this value and that value are the values that we calculated for the standard condition. So what we do is we assume that delta H and delta S do not change significantly with temperature. And it's a fairly good approximation. What it's showing us now is that the delta G is becoming less negative. And so what's happening is that delta G is increasing as temperature increases. There's going to be at some point that delta G actually gets to the positive side and it becomes a non-spontaneous process. Now the conclusion from this calculation is that we can say the reaction is still spontaneous at 400 Kelvin, but a little less spontaneous, if you will. The product side isn't as favored as the reactant side was, or I'm sorry, the product side isn't as favored here as it was at 298 Kelvin. And so what is that suggesting that we can do with this? What it's suggesting is it's going to allow us to calculate a temperature at which the reaction is non-spontaneous. Because remember, those first two calculations before, it tells us that as the temperature increases, well, delta G started increasing. And there's going to be at some point where delta G actually transitions over to a positive value. And remember, a positive delta G is a non-spontaneous reaction. That means that the reactants are favored at that point. It tells us that under those conditions, no matter how long we wait, we will never favor the product side for that particular set of conditions. Well, how do we do that? Well, we have our Gibbs free energy. Actually, from here on out, once you go through the mechanics for calculating those two values, which there's a lot of numbers in Appendix C. There's a lot of numbers you have to calculate on your calculator. There's a lot of opportunity to switch numbers up. There's a lot of opportunity to push the wrong button. And so, getting these two values in place are the two toughest points for these kind of calculations, because there's just so many numbers that can get jumped up as you go through the calculation. So watch out for calculation error when you do those two. But once you have them, what you can say now, notice what I did. And not just what I do, but what chemists do. What do? We say, well, what does this condition mean? This condition means that we're at equilibrium. That means that it stopped moving from one side to the other. It's what I'm telling you when I put a 0 there for delta G. If I solve for T in this particular equation, I plug and chug. This tells me the temperature at which the system is at equilibrium. Well, remember, actually, what you see is that's a higher temperature. We started out 298, we went to 400, and now we're up at 1037 Kelvin. And at each step along the way, the reaction started to favor the products less. And at this point, well, we're at equilibrium. There's no more shift from one side to the other. It's an equal amount on each side, essentially is what you're saying. And so at any temperature higher than that, delta G becomes positive. And so we have a non-spontaneous reaction at that point. And so that's the answer to this part B here. Calculate the temperature at which the reaction is non-spontaneous. And it's anything above 1037. The reaction is actually, it's favored to the reactant side at that point. So that just shows you one of the predictive powers that these thermodynamic parameters have. Now again, we're playing around a little bit with this idea of STP because we are changing the temperature a little bit, and the values of the delta H and delta S do change a little bit with temperature, but we're not going to factor that into our calculation and our discussion for it. Well, what's the phrase? It's beyond the scope of the course, right? We've been talking a lot about this chapter in the context of the equilibrium condition for this particular reaction. There is a link and some equations that connect. Well, this is chapter, this is the chapter we're in now, chapter 19, and then chapter 15, dealing with KEQs, equilibrium constants. And what we start doing here is setting up an equation. Let's go back to the second slide here. the calculations up to this point has really just been dealing with what do you do when only the temperature is changing. And we go through, well, those types of calculations. We still use the standard conditions for delta H and delta S. In the next set of calculations, what we do is now we start factoring in how do we calculate delta G when we're at non-standard concentrations, which, looky there, is important. If you take biochemistry, you will revisit this topic. You will do these calculations in biochemistry. Because, like I said, the concentrations that I always saw in grad school, whenever I was working with proteins or DNA, is always at the level of millimolar, or, well, it wasn't at the level of mole, I'll say that. Millimolar or less, actually. And so we need a way, like I said, delta G has a very powerful predictive property. We can say a lot about the chemical reaction biological systems are very complicated. It at times can be difficult to acquire information about a particular reaction occurring in the cell. If we know those conditions at which they're occurring, then thermodynamics is going to allow us to make predictions based on just calculations. And again, we can start gauging information, understanding information about things that we can't possibly measure directly, okay, or not easily measure directly. That's why I like this chapter so much. I like thermodynamics. And this equation, I'm going to do the same thing the book does to it. I'm not going to derive it. I'm just going to give it to you. Now, I am going to break it down just a little bit. And part of the breakdown, when you look at this equation, you should see a few things that you should see. And let me tell you what I'm thinking about. Well, the naught there should tell us one thing. This is STP, which, right, we've dealt with that. This doesn't have a naught, so this is non-STP condition. And then notice that they've given you this extra factor. R is the gas constant, which for us 8.314 joules per Kelvin mole. T, well, we know that, temp, and then there's our old friend Q. This is the reactant quotient. And just a reminder, this is from chapter 15. This is represented by the concentration or partial pressure of the products initially over the reactants initially. Back in chapter 15, what we did is that given initial concentration conditions, we could calculate this Q, and then we compared it to the equilibrium constant. And so, like if Q was greater than KQ, then it said that the reaction shifts back to the reactant side. There were too many products available or present, and so to reach equilibrium, it go back to the opposite way. And so what we're doing is we're essentially, to calculate this delta G at non-standard conditions, again with respect to concentration or partial pressure, we add this additional component that factors in the initial concentrations. Now, this delta G here is simply this formula that we've already dealt with in many different forms, whether it's calculating delta G naught directly or the delta S naught, the delta H naught for a reaction, the same setup. And so we see this type of reaction playing a role here. So again, we're using tabulated data to predict the Gibbs free change for a standard condition, and then there's this extra little factor that we look at to see how that numerical value is tweaked based on the initial conditions. And let's put this to practice and see what it's going to do for us. So in this problem, we are staying at at the standard temperature anyway, 298 Kelvin. We've dropped the naught, so that tells us something's happened. Real conditions, that's very rarely do you see STP occurring. Let's say in nature. Nature is very complicated. Concentrations vary a lot. They're not going to be exactly at 1 molar. And that's the example here. we have it's the Haber process and for the synthesis of ammonia. So let me just remind you of that equation. Oops, yeah. Equilibrium calculation. Nitrogen, ammonia there. Let's see, we need 3 and we need 2. All gas phase. So we're going to be using partial pressure in this example. There's our expression, or there's our chemical formula. And remember, the reaction quotient looks just the same as KEQ. It's just instead of, I guess I could add initial, i.e. these values that are up here in the formula. I plug them into their appropriate places as shown, and I get a value of 19. Now, I guess, what it's telling us, this initial, without KEQ, it doesn't really help us, tell you the truth. We don't know which way it's going to go. All right. Now, in the context of this problem, it's going to allow us to calculate the spontaneity of this reaction with these conditions at 298 Kelvin, starting with the standard Gibbs free calculation, which is on the next slide. What do you know? So there's our formula again. I'm using the same setup, products, reactants, and notice that for the reactants, both reactants are in the elemental form. That's why we take that to 0. I could have used up a lot of space here and spread this out, but ultimately it's 0. If you look at those tabulated forms, remember delta G and delta H, that starting point is 0 for the formation of the elemental form. And then as it's modified, like ammonia, then you start getting numerical values. So 2 moles times what we grabbed from Appendix C tells us that at standard conditions, meaning rather high concentrate or high partial pressure, 298 Kelvin, at standard conditions, we have a spontaneous reaction. So that's what we're going to see. So now that we have all the components in front of us, we have our delta G at standard conditions, we have our Q value. All we have to do is plug these values into our new expression to get the final answer. And let me do that. I'll deal with the unit change in just a few steps here. I want to keep that at kilojoules. What I mean by that is the R value is in joules, and for the first step of the calculation, I'm just going to leave it as joules. This is joules per Kelvin mole. I'll change it after I do this second half of the calculation that I'm coming up to. Natural log of 19, and so that is equal to minus. Bring that down. Kilojoules. Let's see. The value is, well, the calculator's going to spit out that for joules. And again, there's our, that should send off flags for you, red flags. You got to convert one or the other, and the way I did it in my notes, it doesn't matter which direction you go, is to say this is 7.3 kilojoules. Sig figs, I think I'm using 2 sig figs from the reaction quotient there. And then now the value is negative 26.0 kilojoules. So, as we see, is that 298 at standard temperature at the new partial pressures, this is still a spontaneous reaction. So it's still a favored reaction with this negative value here. So again, that's just a predictive property of delta